Hello everyone. In this session we'll discuss about pressure and then pressure head and then afterwards pressure measurements. We'll quickly revise what is absolute pressure and gauge pressure. You know that absolute pressure is the pressure measured above the absolute zero. Absolute zero is nothing but absolute vacuum. A thermodynamic concept. Absolute pressures are designated with ABS. They will be written in the bracket ABS following the symbol or numerical to distinguish from others. For example, like they say 12 kilopascals is the pressure. Now to say that this is in absolute units, they write a bracket and then ABS. Or if this is the absolute pressure PM, then after PM they write in the bracket absolute pressure. Absolute pressures cannot be negative. That's an important point. Absolute pressures cannot be negative. Gauge pressure is the pressure measured with respect to local atmospheric pressure. Local atmospheric pressure. Now gauge pressures are extensively used in engineering practice and as such are indicated with a symbol or a numerical without any other explanatory notation. In the sense, here they have written 14.0 kilopascals. Nothing has been written whether it is absolute or gauge, but when nothing is specified, it is understandable that it is a gauge pressure. Only if it is absolute, they mention this ABS. Otherwise, if it is a gauge pressure, normally it will be written just like this. And then there is one more example, minus 3.2 kilopascals. It is quite evident that when it is negative, obviously it has to be gauge pressure. It cannot be absolute pressure because absolute pressure cannot be negative. So PM are gauge pressures. Note that gauge pressures can be positive or negative. Negative gauge pressure are also called as vacuum pressures. So vacuum pressure is not complete vacuum. Try to understand that point. Vacuum pressure is slight vacuum is created. Because of that the pressure reduces compared to atmospheric pressure. That's why it is called vacuum pressure. Gauge pressures are commonly measured by Bourdon gauge. Differences in pressures are measured by manometers. This particular equation one can use to convert gauge to absolute or absolute to gauge once you know the local atmospheric pressure. Absolute pressure is equal to local atmospheric pressure plus gauge pressure. Always this is true. Okay. Here one simple sketch wherein we have water surface or liquid surface at this point. It is shown with a triangle and then few lines at the bottom. So it is a top free surface. For example, I have taken liquid. It can be I have taken it as water. It can be any other liquid also open to atmosphere. This is the surface. From here, if we go down, we take it as positive because the pressure increases as you go down. Right? Let the unit weight of this liquid is gamma. If it is water, it will be gamma W. Point of consideration is point A at a depth of h. The point A is at a depth of h from the free surface. Now this free surface, whatever is there, that will be it is under atmospheric pressure. But if we are talking about gauge pressure, this itself is considered as zero. Then afterwards it is added up. So when I write expression for PA, pressure at A, it will be simply gamma into h. Gamma is the unit weight of liquids, then h is the depth. PA equal to gamma. This is a very fundamental equation which will be used very often. PA is the gauge pressure at a point A, h is the pressure head of water at A. Note, as we move down in liquid, pressure gets added up. Hence it is positive. Okay. Here there is a piezometer. Here there is a container. At a point B there is an insertion of a tube and that tube is open to atmosphere. So that is called piezometer. Piezometer is a tube open to atmosphere at one end. The other end is attached to the point where pressure is to be measured. So it is written here, piezometer is a small diameter pipe attached at one end of the point where pressure is to be measured and the other end is open to atmosphere, like this. Point B is the point where pressure is to be measured, the other end is open. Now, not necessary that piezometer is always held vertical. It can be inclined, it can be in a curved shape, but care has to be taken that it will be open to atmosphere. And then what we want is the vertical height difference between this point B and the free surface. Vertical height difference, right? Okay. So piezometer is a small diameter pipe attached at one end to a point where the pressure is to be measured and the other end is open to atmosphere. That is done now. PB, the pressure at point B, is given by the unit weight of the liquid gamma multiplied by the vertical height difference between the point B and the free surface. So this vertical height we have to search and then use. That is what gives the pressure at point B. Okay. So here there are few cases where the pressure head of a particular liquid is converted to pressure magnitude. Now the problem is calculate the pressure in pascals, Newton per meter square, corresponding to, there are three cases A, B, C. First one, 8 centimeter column of liquid of relative density 0.8. So relative density is nothing but specific gravity in fluid mechanics, you should remember. And then specific gravity is nothing but ratio of specific weight of a liquid to specific weight of water. By that definition I can write specific weight of liquid is equal to S into gamma W. S is 0.8 given, gamma W is 9.81 kilonewton per meter cube. Yes, the specific gravity hasn't got any units. Because of that, this product gives you 7.848 kilonewton per meter cube as the gamma 1. Now 8 centimeter column. So this 8 centimeter I have to convert it into meters by dividing by 100 and then use it. So gamma 1 is substituted as calculated, H1 is put as 0.08. Now this is in kilonewton per meter cube, whereas this is in meters. So the units will be reduced to kilonewton per meter square or square meters. Right, the value is 0.62784. Now kilonewton, if you multiply by 1000, it becomes Newton. So 627.84 Newton per square meters, and Newton per square meters is nothing but pascals. So the pressure is equal to 627.84 pascals. This is given as 8 centimeter column of liquid of relative density 0.8. That is same as 627.84 pascals. The second case, case B, that is 6 centimeters column of mercury. Now mercury, I know the specific gravity is 13.6. How to calculate specific weight? By knowing specific gravity, gamma m is equal to S into gamma W. S is known, gamma W is known. 133.42 kilonewton per meter cube would be gamma. The height is given 6 centimeters, so I'll substitute it H as 0.06. So product gives you 8.0046 kilonewton per square meters. If I want in Newton per square meter, I have to multiply by 1000, so it becomes 8004.6 Newton per square meters, or 8004.6 pascals. That is the pressure. So rather than telling 8004 0.6 pascals, it is easy to tell 6 centimeters of mercury. That's why pressure is given either in pascals or column of particular liquid. You can just see here in 3 cases 3 different liquids have been used, right? Now 6 centimeter column of mercury is different than 6 centimeter column of liquid of a particular specific, or 6 centimeter column of water. It will be different because gamma is varying. Now the third case, 2 meters of column of water. So again the same steps, gamma m is equal to S into gamma W. S is 1 because it is a water, so gamma becomes gamma W itself into 2 meters, 19.62 kilonewton per square meters would be the pressure. Okay, here we'll stop. Thank you. Hello everyone. In this session we are going to discuss in length about manometers, the devices with which the pressure is measured, the most fundamental device with which the pressure can be measured. We'll see overall view of the other devices to use the pressure measurement, and in depth about manometers. Okay, a manometer is a device to determine the pressure in fluid by balancing the pressure against a column of liquid. So it is a device to determine the pressure, first of all, in a fluid by balancing the pressure against a column of liquid. So this is how it is done. That is what is manometer. Now in a manometer, the basic point to remember is that in a continuous mass of same static fluid, the pressure at the points in any horizontal plane will be the same. There are two things here. Horizontal plane is one, but it should be the same static fluid medium. If the fluid medium is different, then the statement is not true. We'll see, of course, when we solve the problems what this statement actually means. Now, overall view, measurement of pressure is done by, there are so many things: barometer, simple manometers, board on gauge, pressure transducer. Now, barometer is a device which is used for measuring atmospheric pressure. We have done all this earlier. You can revise. Simple manometer is new. Simple manometers are used to measure intensity of pressure at a point. They are connected to a point at which the intensity of pressure is required. Such a point is called gauge point, means the point where the pressure is being measured. Okay, now types of simple manometers, we have got piezometers, U-tube manometers, single tube manometers, and inclined tube manometers. We'll go into the details of all these manometers. So here there is a piezometer. Piezometer is used to measure the gauge pressures of a fluid. This is exactly similar situation we already done. Point A, pressure at point A is equal to, when I put this, what is the height at which the free surface goes up? That is h. H is the vertical height difference between the point at which the pressure is required and the free surface. Hence it is gamma into h, where gamma is the unit weight of the liquid. So piezometer consists of a glass tube inserted in a wall or a vessel or a pipe at which the point at which the intensity of pressure is to be measured. The other end of the piezometer is exposed to atmospheric air. The height of liquid in piezometer gives the pressure head from which the intensity of pressure can be calculated. To minimize the capillary effect, we have seen what is capillary. When you insert a tube, automatically the water rises up or goes down. So to not to have the error because of the capillary action, the tube has to be, minimum size of the tube has to be 12 mm, so that you don't have much of the effect of capillary. So to minimize capillary rise effects, the diameter of the tube is kept more than 12 mm. That's what is the limitation of manometers or piezometers, you can say. So here there is a view. The section of the pipe is there. This is the pipe. A pipe with a liquid inside. The point is center point P. C is the point where pressure is required. So this tube is inserted, which we call it as a piezometer. The shape of tube, orientation, inclination, size are nothing to do with the pressure. So what is the size, what is the material, what is the shape, all these things do not matter. What is the matter is the point C and the free surface. What is the vertical height difference? H is the vertical height difference between the free surface of the liquid and the point at which the pressure is required. So that is required. Once you know HC, once you know the gamma of the liquid, then PC, the pressure at C, is equal to gamma into HC. Of course, this is gauge pressure, right? So this tube is known as now piezometer. Tube open to atmosphere at one end, and this is free surface. Okay. Once more the same piezometer is shown, but here there is two types of liquids. One is the water or whatever liquid that is flowing inside the pipe itself goes up, and then above that again they have put some other liquid, gamma 2. When you have such an arrangement, obviously the unit weight or specific gravity of gamma 2 has to be more than gamma 1, less than gamma 1, then only it can float. Otherwise what happens is it sinks inside. So gamma 2 is lighter, or specific gravity is less than the specific gravity of this liquid. Okay, so this is the free surface of liquid of specific weight gamma 2 open to atmosphere. The top free surface is under atmospheric pressure, but it is considered as zero in gauge pressures. So this tube is known as piezometer. Here H2 is the height of gamma 2, H1 is the height of gamma 1. Now as we move along horizontal plane in the same static liquid medium, the pressure does not change. Means here we want point D, you can consider any of these points, right? Everywhere here the pressure remains the same all along this plane. That's what it means. Even at this point, the pressure is same as point D. Okay. Now as we move down in the liquid medium, the pressure gets added up, and as we move up, the pressure decreases. So here let us say this is pressure D, and then as we go up the pressure decreases, so I have put negative sign minus. And in gamma 1 liquid we are going through a distance of h1, so minus gamma 1 h1. Further up again I move in gamma 2 for a height of h2, up I am moving, so minus gamma 2 h2. What I will reach here is the open to atmosphere, that is to say pressure of atmospheric pressure, which is taken as 0 for gauge pressure. It is equated to 0. So we can rewrite this equation as PD equal to gamma 1 h1 plus gamma 2 h2. Alright, and then whatever calculation data will be given, that will be substituted and calculated. There is one more way, or I have written. So here we can start from here and then go down. I have considered here PD will be absolute pressure. Here I have taken atmospheric pressure as 0. The PD calculated from this equation will be gauge pressure. PD calculated from this equation would be absolute pressure. Now in this case also, if you substitute this atmospheric pressure as 0, you will get almost the same equation. PD equal to, you can just see here, gamma 1 H1 plus gamma 2 H2. Now how to write this equation, I'll explain. Okay, this is atmospheric pressure, P atmospheric pressure. Then I go down. When I go down, the pressure gets added up in gamma 2 for a height of H2. So that's why I have written plus gamma 2 H2. Further I go down, again plus in gamma 1 through a height of H1. What I'll reach at this level. At this level there is a point D, so the pressure at point D will be the same. That's why it is equal to PD. That's how you have to analyze the piezometers. Okay. Here a variety of piezometers are given. This just now we have seen. If there is a point at which the pressure is to be measured, okay, you insert a tube which is known as piezometer, and there has to be a scale to measure vertical height difference between the point at which the pressure is being measured and the free surface liquid. Here it is H shown as. So from a pipe we can take a point to measure the pressure, or even from a tank, if you want the pressure measurement, you insert a tube and then allow it to go right up to free atmospheric pressure level. Here also the level difference, vertical height difference between the free surface and the point at which we need the pressure has to be measured. It is H again here. If you want X at the bottom of the tank, you have to go down little more actually. It is not just H, plus this much also. Now this is the arrangement for calculating or measuring negative pressure. This is up to atmospheric pressure. It is to measure the pressures more than atmospheric pressure. It's a reverse piezometer, you can just see here. So this is to measure vacuum pressure. We'll see when we solve some numerical problems, we will understand this. Okay, here I have one problem. An open tank contains water to a depth of 2.5 meter and an oil of relative density, that is specific gravity, 1.25 to a depth of 1.5 meters. Determine the pressure at A, the water surface, at the oil and water interface at a depth 3.5 meters below the free surface at the bottom of the tank. So here we have to draw the figure. I would suggest everyone to practice this drawing whenever we try to solve the problem. Looking at or reading the problem, you should be able to make out what is given and how it is, and after drawing the sketch, then only we'll be able to analyze for pressures. Now anyway, it's an open tank, it is said. Fine, I have drawn. Now which liquid is above, whether water is above or oil is above. Now we know that specific gravity of water is 1 and relative density, oil of relative density 1.25. So obviously oil has got more specific gravity, because of that it goes down below the water surface, and it stands for 1.5 meter. So we'll show 1.5 meter for the oil of specific gravity 1.25. Then we have got water 2.5 meter. Then there is a free surface. Determine the pressure at A. So I have denoted A, then B at oil water interface, then C 3.5 meters, because total distance up to the bottom is 4 meters. So here there is a point C 3.5 meters below the free surface. There the pressure is asked, and then finally the point D. So these are the points where the pressure is being asked. Now how to solve the problem? I'll give you the hints. You have to solve the problem on your own. Now pressure at A, so this is the free surface. If we are talking about gauge pressure, that is atmospheric pressure is taken as 0, then pressure at A is equal to 0. Simple. Pressure at A, free surface, is equal to 0. This is gauge pressure. If you want absolute pressure at point A, then it will be equal to 101.325 kilopascals. That is atmospheric pressure. Right? Now we'll talk about all these things in gauge pressures only, because atmospheric pressure is taken as 0. Okay. Now at the oil interface, in the sense point B means at a depth 2.5 meters below, then I use P is equal to gamma H. Here it is gamma 1 H1. Gamma 1 is water, 9.81 kilonewton per meter cube. Height is 2.5 meters. So we'll be getting PB, the pressure at point B. Then at point C, if we want, this is already 2.5 meters, and this depth, additional depth, will be 1 meter. So when I write an expression for PC, I'll start from here, right, 0. Then I'll go in water for 2.5 meters. So 9.81 into 2.5 plus the unit weight of this liquid would be S into gamma W, 1.25 into gamma W, through a distance of 1 meter. That's equal to PC. And if you want at the bottom D, then it will be again 0 plus gamma of water into 2.5 plus gamma of oil multiplied by 1.5. That should be equal to PD. So I hope you will be able to calculate all these things. Okay, here YouTube manometers are there. There are so many examples, figures are given. YouTube manometers. Right, there is a pipe. X is the point where the pressure is to be measured. It goes down and then it takes the shape of U-tube. Right, here also there is a U-tube. Here also there is two. Now there is a different liquid which will be used for measurement of pressure, which is known as manometric liquid. And obviously the specific gravity of this manometric liquid will be quite high compared to the specific gravity of the liquid which will be flowing in this pipe or so, because the pressure is more. If we insert simple piezometer, the height for which the liquid goes up will be too large. Now to reduce that large height, what arrangement is done is a U-tube manometer is used with a heavy specific gravity manometric liquid. Generally the manometric liquid used in U-tube manometers is mercury. Right, now how to analyze, we'll see here. Here I have a point A. This liquid is gamma 1, having a specific weight of gamma 1, and the tube goes this way, and here there is gamma 2. Manometric liquid unit weight or specific weight is gamma 2. Right, now this specific gravity is chosen more for more pressure, less for lesser pressure. That's how the manometric liquid is chosen. Now here the point to be observed here is, here there is a water which comes and stops. Here the gamma 2 or liquid 2 starts. Now at the point B and then at the point C, we got the same liquid if you consider the bottom portion, and because of that, pressure at point B is equal to pressure at point C. That's what is written. Means this is static liquid in the same liquid medium in a horizontal plane, the pressure remains the same. That is what the first slide statement. Right, if we move horizontally in the same liquid medium, right, the pressure remains the same. That is why PB equal to PC. That is a point. Okay, U-tube can measure negative pressures. U-tube can also measure negative pressures. Fine. Now gauge fluid selected means manometric liquid. Gauge fluid selected for sensitivity. It will be dense for fluids, dense fluids for high pressure, and thin fluids for lower pressure or low pressures. Now how the equation is written, we'll just go through. We'll start with a point P, A, right? Point A, P. When I move horizontally, there is no change in pressure in horizontal because this is also gamma 1 liquid, liquid number 1. So as we move horizontally with these dotted lines, at this corner, whatever pressure is there at A, the same pressure is there at A. Now when I move down, pressure adds up. So that's why there is plus. And we are going down in same liquid gamma 1 through a height of h1. That's why it is gamma 1 h1. Now this point B we have reached. This is same as point C. Then afterwards I'll go up. That's why minus. In what liquid? Gamma 2 liquid for a height of h2. That's equal to, when I reach here, it will be equal to 0. That is, atmospheric pressure is considered as 0. Okay. Now from this equation one can write PA is equal to minus gamma 1 h1 plus gamma 2 h2. Okay. So a U-tube manometer consists of glass tube bent in U shape, one end of which is connected to a gauge point and the other end is exposed to atmospheric pressure. You can just see here. U-tube consists of liquid of specific gravity other than that of fluid whose pressure intensity is to be measured and is called a manometer. Means this liquid will be having a different specific gravity. We have seen it here, how it is more or less depending upon the pressure intensity. But you cannot have the same liquid here. That is what the point is. Otherwise there is no fun in using U-tube manometer. It becomes simple manometer, simple piezometer. Only when you use other liquid, then it becomes really a U-tube manometer. Okay. Okay, manometric liquids. This is about manometric liquids. What are the properties that are to be exhibited by manometric liquids? Examples. Manometric liquids should neither mix nor have any chemical reaction with the fluid whose pressure intensity is to be measured. Obvious it is, because at the interface if the reaction starts, then there will be a problem here at the interface. This manometric liquid should be inert enough to not to react with the fluid there. Then it should not undergo any thermal variation. When the temperature decreases or increases, there shouldn't be any change in the volume too much. Right? Manometric liquid should have very low vapor pressure. Then manometric liquid should have pressure in sensitivity depending upon the magnitude. In the sense, if there is a high pressure, what should happen? If there is a low pressure, what should happen? That sensitivity should be there. Now of the pressure to be measured and accuracy required. If there is a high pressure required measured, then mercury would be the better. If there is a low pressure measurement, then it would be better to use the manometric liquid having specific gravity less than 1. Right? So examples of manometric liquid are mercury, the first one. Then carbon tetrachloride is also used, which is having specific gravity something like 5, 6, I don't remember exactly. But mercury has got 13.6 as the specific gravity. Because of that one can use it. So here we'll stop. It's a U-tube manometer or inclined tube manometer. Inclined. Look at the shape. Inclined tube manometers. Now if there is a vertical tube in this, the height would have been, look at this level, from this to this. If I call it as H2 would be the vertical height difference. But suppose this is too small to measure, then the error involved in measurement would be too much, because we have to increase this length. What is done is it is made inclined so that the length of the liquid will be more. Okay, inclined tube manometers are used to measure small magnitude pressures. To increase the accuracy, the length of the column of liquid is increased by making it inclined. Now, how to write expression for the pressure? It is same. You move horizontally, no change. You go down, you add up in gamma 1 through height h1, gamma 1 h1 plus. Now from this, I'll move on this side. Look at this. It is the same liquid, because of that I can move, come here. Then here to here I can write it as L2 sine theta, because this angle, right, the vertical height in this triangle, if you can imagine a triangle like that, right, this will be hypotenuse L2. This angle over here would be H2. I'll try to draw, that will be better for you to understand the things. So here, this one, this angle is theta. Inclined length is L2, because of that this becomes L2 sine theta. This is S sine theta. Oh my goodness, look at that. Anyway, L2 sine theta would be the opposite side. L2 theta, L2 sine theta. That's why I have written gamma 2 L2 sine theta, but we are going up here. That's why there is a negative sign. And when you reach the top, this is atmospheric pressure level. That is equated to 0 to measure the gauge pressure. So from this equation, I can write PA is equal to minus gamma 1 H1 plus gamma 2 L2 sine theta. Okay, here we'll discuss about pulled-on gauge. These are mechanical devices which are used for measuring the pressure. Almost everyone might have seen these gauges, pulled-on gauges. Whenever we fill in air for our vehicles, we fill and then we look at the magnitude, something like 32, 33, right? So that those are the red numbers that are printed here, and then units used are PSI, pounds per square inch. So generally we require 32 or 35, so somewhere there. But if you want to use kg per centimeter square as the units, it will be hardly 2 point something, right? Almost 2 kg per centimeter square, right? So when I want to have 32 or 35, I have to tell that it is 2.05 or 2.08. So this specification 2.08 or 2.1 kg per centimeter square would be difficult for communication. That's why still in use is this 32 or 35, that is PSI is the units used. Anyway, that's about units of measurement. Now what is this gauge? Actually this is the front view of that. So here also both the front and back views are given. So front view is the dial gauge with a needle, but inside that, if you just remove this dial, what is there inside is like this. So this is the pipe which connects to a point where pressure is to be measured. Okay, now this has got, look at this, another pipe which is going that way, right? This is indicated, this itself is called as bolt-on pipe. Now when the pressure is more, this pipe, actually it is a free pipe, this tries to enlarge, and because of that it actuates the needle to move, right? We'll see this in detail in the next slide. Okay, here a better view of the same thing, right? So this is pressure inlet. Here there is a pipe which is bolt-on gauge tube, right? The cross section of this is oblong, you can just see here. Then when it is the pressure is allowed in this pipe tries to straighten up, and because of that it moves that way, this point moves that way, or this link will pull it up. And because of this pivot, what happens is this goes down. When this goes down, this rotates and then reading goes up. So that's how the board-on pressure gauge works. The same thing if you want to draw in your notebook, this is how you can draw. This is the pressure point, this is board-on tube. This gets enlarged when the pressure is let in. Section of this tube is something like that, it is shown here also. Now this is a link, the important part of the device. Here this is the pivot point, fixed point. When this moves, this is pulled, because of that this goes this way. When this goes this way, this rotates and then the needle shows higher values of pressure. That's how this operates. So board-on gauges, device used for measuring gauge pressures. The pressure element is a hollow curved metallic tube. Hollow curved metallic tube closed at one end, the other end is connected to a pressure to be measured. So here it is closed, the other end is connected to a point where the pressure is to be measured. When the internal pressure is increased, the tube tends to straighten, pulling on a linkage to which it is attached to a pointer and causing the pointer to move. So this straightens up, pulls the linkage, rotates this pointer to higher value. When the tube is connected, the pointer shows 0. The board-on tube sketched in figure, right? It can be used for the measurement of liquid and a gas pressures up to hundreds of MPa, hundreds of megapascals. Mega is 10 raised to 6 pascals or 10 raised to 3 kilopascals. Means up to 1000, hundreds of thousands of megapascals can be measured by using pressure gauges. Of course, different different ranges of pressures can be measured with different board-on pressure gauges. Okay, thank you. We'll stop here.